Here is a bar magnet with a north and south pole. Running inside the magnet will be lines of magnetic flux density field, which will then emanate outside the magnet. Here is an illustration of those lines of magnetic flux density. So they'll emanate out the north pole and around the magnet and then back in the south pole. And you can see that the spacing between the magnetic flux density field lines will decrease as you move away from the magnet, indicating a reduction in strength of the magnetic flux density field. Here I have a galvanometer and I have it connected to a 100 turn coil. So whenever there's a changing magnetic flux with respect to time inside the coil, there will be an electric field generated, and that electric field inside the coil will result in a current flow. So when I take this bar magnet and move it towards the coil, there's an increase in magnetic flux with respect to time, and I see a positive current generated. Now when I remove the magnet, there's a decrease in magnetic flux with respect to time, so I have a current flowing in the opposite direction. And the current that's generated is proportional to the rate of change of magnetic flux with respect to time. So I move the magnet slow, I get a small current. If I move it fast, I get a larger current flowing. I was asked the question, what would happen if instead of moving the magnet into and out of the coil, I was instead moving it around outside the coil? Well, as long as I'm moving the magnet, I am getting a change in magnetic flux with respect to time inside the coil. It's just that that change in magnetic flux with respect to time will be small because the magnetic flux density field falls off with distance from the magnet. But if you watch closely, when I'm moving it lateral to the coil, you can see a little bit of movement of the needle indicating I am generating some current. Similarly, if I'm moving it alongside the coil like this, again I'm getting some change in magnetic flux with respect to time, and you can see a little bit of movement of that needle indicating a little bit of current being generated. Now the current generated is going to be proportional to the change in flux linkage with respect to time, which is the product of the change in magnetic flux inside the coil and the number of turns of the coil. So if I greatly increase the number of turns of the coil, then when I move the magnet outside the coil, I should be able to generate much more current. So here's a coil I wound that consists of 30,000 turns. So for the same changing magnetic flux inside the coil here, I'm going to get a much greater change in flux linkage. So let me now connect this 30,000 turn coil to the galvanometer. So now even when I move the magnet slowly, I generate current because of the large change in flux linkage with respect to time. So I have to be careful not to move it too fast and damage my galvanometer. Okay, so now let me move the magnet laterally. So you see there was a current generated because there was a changing magnetic flux inside the coil. So as I'm moving it towards the coil, there's an increase in magnetic flux, and I was generating a positive current. Now as I continue to move the magnet and away from the coil, now there's a decrease in magnetic flux inside the coil and a negative current generated. So now I'm going to take the magnet and move it alongside the coil. So as I'm moving it towards the coil, I noticed I was generating a positive current, and as it continues to move away, now it's a negative current. So as I'm moving it towards the coil, I'm generating an increase in magnetic flux and a positive current flow, and now as it's moving away, I have a decrease in magnetic flux and hence a current flowing in the opposite direction. In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. I have an ammeter here, and I have 3 coils. I have a coil with 1 loop, 10 loops, and 100 loops. I also have a bar magnet, and I will start by connecting the single loop coil to the ammeter. I now have the single loop coil connected to the ammeter, and I'm going to move the bar magnet into and out of the coil. And if you watch very closely, you can see a slight deflection of the ammeter needle. Okay, so now let me connect the 10 loop coil. And then I'm going to do the same thing. I'm going to move the bar magnet in and out of the coil. Now you can see more movement of the needle. In fact, if I go very slowly, you see just a little bit of a deflection. And if I go quickly, you see a greater amount of deflection. Also, as the magnet is going in, the needle deflects to the right. And as I pull the magnet out, it deflects to the left. But when the magnet isn't moving, there's no deflection, indicating no current flowing. Okay, so when the magnetic field is changing going into the coil, there's a positive current flowing. When it's changing coming out of the coil, there's a negative current flowing. And now let me connect the 100 loop coil. And I'll start by moving the magnet in very slowly. You see a deflection to the right, pull it out to the left. And if I go in quickly, you see a much greater deflection. Okay, so the rate of change of the magnetic field affects the current also. We saw that as the number of turns in the coil increased, the current increased. So the current is proportional to the number of turns, which we'll use N to represent. We also saw that the current increased as the rate of change of magnetic flux inside the coil increased. So d psi dt represents the change in the magnetic flux inside the coil. Now, if we were to monitor the resistance of the whole circuit, that is of the coil and the wires and the ammeter, we would find that the current was inversely proportional to the total resistance of the circuit. Now, this equation is usually written as I is equal to minus N over R d psi dt, and we'll talk about the significance of this minus sign in a future video on Lenz's law. So now if we multiply both sides of the equation by R, we get Ri equals minus N d psi dt, and resistance times a current is a voltage or a potential. We call that the electromotive force. And so the electromotive force is equal to minus N d psi dt, and this is known as Faraday's law. Here's an illustration of the way Michael Faraday actually performed the experiment. He had a coil of wire that he attached to a battery, so the current flowing through this coil generated a magnetic field. So that was the magnet he used, was an electromagnet. He had a coil with a larger diameter that was attached to an ammeter. So then by moving the electromagnet in and out of the larger coil, he could detect the induced current on his ammeter.